So next, I have evaluated the performance of all the algorithm or the models in the form of a couple of matrix. So the first matrix is called the R-squared score, okay? And the R-squared score goes back to its roots from statistic or applied statistics. And it is a metric that really means what percentage of the variation within the data is explained by the model. Okay. And here the way to interpret the metric is the more the percentage, the better it is. Okay. So here I have created the R-squared score for all the 6 algorithms. And then I have printed them against each of the model. So here it looks like linear regression has only explained around 72 or 73% of the variation within the entire data, okay? Which is kind of respectable, however, not a very decent one. I'm not even going to talk about the support vector regression because this looks so bad. Decision tree has covered around 70%, wherein the last 3 has been nearly effective, right? The random forest regression has got a very respectable percentage of variation explained, which is over 80%, almost 81%. When it comes to the extreme gradient boosting regression, it has also covered around 78. However, the winner is definitely the gradient boosting regression model because it has covered more than 82% of the variation, or it has explained above 82% of the variation within the data set. So I'm glad that my visual cue was kind of up to the mark, okay? But that's not all. This is one of the very strong methods of identifying the model performance. But I'm still going to do one more round of evaluation. And this time I'm choosing another metric called the mean absolute error. Mean absolute error is another method of identifying how each of the model has performed the predictions. Okay. So the way this metric works is for each of the record in the test set, the algorithms have done a prediction, right? And in this mean absolute error method, I have taken the actual value of each record and the predicted value of each record. So let's say if the actual value for a record is 100, and if the predicted value of a record is 120, then I'm going to take out the difference of number between these two. And in this case, it will be 120 minus 100, so 20, right? Similarly, I'm going to do that for all the records which are passed on the test data set. And I will keep adding the number of differences between them. And once I've added all of them, then I'm just going to take the average out of it, the arithmetic mean. And that exactly is going to be my mean absolute error. So in this case, the less the error, the better it is for the model, right? So here I have exactly done the same thing. I have just created the mean absolute error metric for all the different algorithms for all 6. And when I have printed it against all the model names, I can see linear regression has over 4,000 as a mean absolute error. Support vector regression has a lot more. Decision tree has less error, where the random forest has around 2734. Gradient boosting has 2757, and stream, the EGBR, the extreme gradient boost, has around 3000. So it is a very tough competition between the random forest regression and the gradient boosting regression. They both are almost same. Perhaps maybe random forest is doing better by a very slight amount. However, by comparing both the matrix, I am going to go ahead with the gradient boosting regression. And the reason being, it is able to explain a slightly higher percentage of variation within the entire data. And that is the most important piece here, because the business goal is that the application needs to be able to predict the potential insurance coverage cost associated with each of the application. And the more number of applications I'm able to correctly predict, the better it is for the business. And therefore, I'm going to go ahead with the gradient boosting regression.